start recording here. Yeah. Okay. So, in the last few classes, we have been working a bit on partial differential equations, right? So, the idea is not so much that this is something complete or something very thorough, because of course to do that will take several months, right? But I hope that at least some exposure to partial differential equations and a way to simulate them would make you more comfortable with those, right? Because this is it's a very nice modeling approach, and a lot of stuff that you essentially sometimes you're kind of forced to use PDEs, right? There are some problems that are hard to do with only ordinary differential equations. And then, you know, like ecologists can do it too, yeah? Yeah, so that's that's the message, right? So you don't have to leave it all the fun to the physicists, right? So, so now what I'm going to do is going a bit further on that note, right, on PDEs. And today, I'm going to talk a little bit about stationary solutions to PDEs, right? So, so you remember that when we studied ordinary differential equations, right? So I'll do the first part on the board, right? I think it's nicer, yeah? So when we had equations like, I don't know, dn dt equals some function of n, or maybe you had a system of equations, I don't know, dn1 dt equals some function of n1 and 2, and then dn1 2 dt equals another function of n1 and 2, like for instance, consumer resource equations or competition equations, right, or something like that. One of the basic tools to study these equations is looking at the equilibrium solutions, yeah? How do you look for equilibrium solutions? You look for points where this stuff here is equal to 0, right? It means that if you start at this value n star, you stop there, yeah? And the same for these equations here. You transform this system of ordinary differential equations. You look for where this is 0, okay? And now you have a system of two. This now, this 2 here, right? So this 2 equations here is now a system with 2 equations and 2 variables, yeah? And of course, the fixed points, they give you a lot of information. They're not the end all of everything, right? Because you remember that some fixed points can be unstable, some fixed points can be stable, and that changes. Yeah, the solution goes can go to the stable fixed points. Sometimes there are systems like consumer resource models that you studied that all the fixed points were unstable, right? Because the actual solution, long-term solution, is not a fixed point at all. It is an oscillation, right? It's a cycle. Okay, and then the cycle is stable and the fixed points are unstable. But even in those cases, knowing the fixed points is helpful, right? Because of course, okay, there are cycles here, but the cycles oscillate around the fixed point. Yeah. So if you know where the fixed point is, you know around which point the solutions will cycle, right? So this even in that case, you do have more information by looking at the fixed points. Okay. So the first thing we are going to see now is how to solve this numerically, okay? Because so far you have done most of these calculations either by hand or using SymPy, right? But then this, as you have seen probably in your own problems, right? Sometimes you don't have those equilibrium solutions so easily doing by hand, yeah? Some of you have this experience already of, yeah, looking for solutions, yeah, and not finding them by hand, yeah, or even with SymPy or something else, right? So you can do this numerically, okay? Yeah? And then we are going to look at partial differential equations, right? In particular, we are going to look at the Fisher-Kolmogorov equation that we have been looking at previous classes that was like this. So it was, so we had a growth term that is just the logistic growth, and you have a diffusion term that is like this, yeah? And this in a region, I don't know, from 0 to L, okay? And what does this describe? This describes a density, I don't know, something like this, a density of population in terms of the position x here. So this is the x is over here, yeah? In terms of x, and this density changes over time, right? But then what is the equilibrium solution for this? Is a solution in density over here that doesn't change with time. So the analogous situation of this fixed point here would be solutions where this is equal to 0. Okay, this is equal to 0. So you don't have you no longer have a time dependence. You only have spatial dependence, right? And now you see that the stuff that is left here, right? So my n star here, right? So my n star here. Now n star is now a function of x. Yeah, a function of x, but not of t. Okay, so it depends only on space and not on time. Yeah, so this would be an equilibrium solution for this reaction diffusion equation, right? And it turns out that in many problems, it is easier to compute this solution here than to simulate for a long time this equation over here. Okay, so it's sometimes it's more convenient. Sometimes it saves you from very thorny numerical problems, okay? So, and so you can go directly to the equilibrium solution. But then, again, you have to be careful that sometimes you have that equilibrium solution actually is the stable solution, the final solution for a long time. Sometimes it may not be, right? So you are always bound to also solve the time-dependent equation just to check that that equation really is the attractor, right? The solution where the population goes for a long time, okay? Yeah? Okay, so the idea then is, okay, how will we solve this thing here? Because now, you see, if you look at this here, there's a derivative here, yeah? There's a derivative here, right? And then I told you that now n star is now just a function of x and not of t, right? So I don't need a partial derivative here anymore. Yeah, this is now a regular derivative, right? So this equation here, I can actually write it as something like, just write it like this. G dot d2 dx squared plus r n star 1 minus n star over k is equal to 0, okay? And this is an ordinary differential equation, yeah? It's an equation that involves the derivative of n as a function of x, okay? And then we are we can think of this as, well, this is an ordinary differential equation. We know how to solve this, right? Yeah? We just use ODE int and so on. Yeah, that's right. Yeah, looks like it will be easy, right? But there's a problem, right? Because now, you see, this is a second order differential equation, right? Second order, okay? Second order means that you have to have two initial conditions, right? So it's, instead of having just the initial population, to use ODE int, you would need to have the initial population and the initial derivative of the population at some initial location. But that's not what you have here, right? Because, why? Because this equation here, it came together with boundary conditions. Remember the boundary conditions? Boundary conditions. What were the boundary conditions, right? So, for instance, one of the boundary conditions that you use is, well, we want to say what happens at 0 and at L, okay? So one of them, for instance, is if I put both of them equals to 0, right? So n at 0 is 0, and this is also n at L for any time, right? So it's also 0, okay? So this gives me two conditions, right? Two conditions that n star is all, because this is valid for all time, my equilibrium solution also has to satisfy this, yeah? Okay? But then this gives me two conditions that don't show up at the same value of x. I have a condition for n at 0 and a condition for n at x equal to L. Yeah, so this is a different, is actually a completely different kind of problem than what we have been solving before. Yeah? Okay, so this kind of problem here, right? So when you have a differential equation together with these boundary conditions, okay, this is what is called a boundary value problem. Okay, so this is what is called a boundary value problem. Okay, and it turns out that to solve this kind of problem here, it is easier to try methods similar to what you do here than what you usually use to solve differential equations, right? So what do? You essentially try to discretize this in space, okay, in the range of from 0 to L. You discretize this in space, and then when you discretize this in space, you will have an n star at some point here, some point here, some point here, and so on and so on, okay? And then this becomes a set of algebraic equations. And you kind of end that here, okay? What is the difference? Is that here, if you want an accurate solution, you have to have a lot of points, okay? We were using something like 100 points, okay? Yeah? Then I will need a solver that can solve not one equation or two equations. I want a solver that can solve hundreds of equations at the same time, yeah? So this is, yeah, this is interesting, right? Yeah? Okay, so let's look at how to do this in the computer, okay? Questions? Questions? Comments? Is that more or less clear? So I didn't go yet into the details of how we are going to do this exactly, but the general picture is okay? Yeah? Okay, good. So, so let's switch here to the computer, or maybe let me just keep the board over there. Okay, so so this first part here is pretty much what I just told you about, okay? And let me just check that it's all here. Maybe I forgot something. I don't think so. Yeah. Okay. So this is the equation we want to solve, right? And the idea is that we can find this equilibrium solution without solving the full PDE, right, over time. Okay, so let's just start with a single equation, right? So this is actually a toy problem, because usually if you have a single equation, that's usually the nice case where you can do it by hand. Okay, but then let's do this just to train, to learn how to use the method, okay? Okay, so this is our Lie effect model. Do you remember that? Feels like 1,000 years ago, yeah? So, yeah. It's just 3 weeks, right? So, yeah, so, okay. And now I'll choose some values for A, for carrying capacity, and for this threshold value for the Lie effect, okay? So I have R equals to 2, K equals to 100, A equals to 3, and so on. Okay, and now we want to see what are the equilibria, right? Of course, the equilibria, this is already factored, right? So the equilibria will be 0, 100, and 3, right? So where each of these factors are 0, okay? But then let's read over this with our function, okay? So we will use this function called fsolve, okay? Or function solve, that receives two values, okay? Two objects, actually, right? So the first thing will be a function that returns the thing that we want to solve, okay? So this is a function that receives m and returns this stuff here, yeah? And it will look for which values of m makes this equal to 0, yeah? And the second value that you pass for it is the initial guess, right? So this is where it becomes tricky, okay? Where it becomes tricky because you have to guess you have to guess something for the search to begin. And depending on the value of the guess, you will find different solutions, because I have here 3 different solutions. You see? So now you see that this is already not so easy, okay? So so let's see how it goes, right? So here I import NumPy, import this function fsolve that is inside this submodule of SciPy that is called optimize. And here we have our function, right? So 2 times x, 1 minus x over 100, x over 3 minus 1, okay? And now I pass to fsolve this function f, and I pass an initial guess, okay? So I tried here with 0, 1, 1, 2, 10, 50, 80, 150, okay? So what solution is each of those guesses arrive at, right? So let's run this and find out, okay? Well, first running always takes a bit of time. Yeah? Okay, so if I start with those two first guesses here, 0, 1, and 1, it finds the 0 equilibrium, right? So n equals to 0. If I start with 2 or 10 or even 50, it goes to 3, okay? It goes to the second equilibrium. And if I start with 80 or 150, it goes to the carrying capacity 100, right? So you see that it's not even going for the what would be the closest one. Yeah, it goes for just something, right? So it's really hard to predict where it's going to end up. Yeah, question.
On our basic model for the Allee effect, wasn't the population below A supposed to go to extinction?
Yeah, exactly. But it's not solving the system. It's not so. If you start with an initial condition, you always go either to 0 or to 100. Okay, with an initial positive initial condition. Okay, below 3 it goes to 0, above 3 it goes to 100. But this is not solving the system of the equation, the differential equation. It's just looking for where this function gives you a 0. Okay, even if it is unstable. So this method is going to find unstable fixed points as well. Okay, yeah. Okay, but then the issue is that you don't know for which initial conditions it will arrive at which solution. Okay, so it's a good idea to more or less know beforehand how many solutions you expect, which solutions are there more or less, you know, even, and then it's easier to try to guess to arrive at the solution you are looking for. Okay, so for single equations, okay, when you have a single equation, of course there are other methods that you can, if you have a single equation, and plot this function here, okay, and it can tell you something like, for instance, in this situation, something like this, right? You know that you have this positive region, this negative region, this positive, this negative, and you know that between each positive and negative, so this is f as a function of n. Okay, so I just plotted the Allee growth rate here. You know that between each of those regions, there's a 0, and there are other methods besides fsolve that instead of putting a single number, you can give it two numbers, right? One where it is positive and one where it is negative, and it's going to find the equilibrium point, the fixed point in the middle, okay? But this is, and then there are programs, there are methods to try to find all of the solutions in a systematic way for a single equation, okay? So this is not, but then this is only actually works for when you have a single equation, right? And when you have a single equation, this is really the not so interesting situation, because usually these are the ones that you can solve by hand, okay? Or, yeah? Okay, so yeah, you can systematize it to make a more systematic approach to find all solutions and so on, but that's not very useful, okay? Because these are the easy systems, okay? So this doesn't generalize well for more than one equation, okay? So I won't discuss this at all, okay? Okay, so yeah, so I was doing this just to illustrate how to use fsolve and how the solution depends on the initial conditions, the initial guess, okay? Not the initial condition. Okay, so let's try something more, something harder, okay? Something that you wouldn't be able to do by hand, okay? So I wrote here a nice system of equations. What do you think about this? Yeah? So this is a two consumer, two resource system. You see, two resources, two consumers with functional form type 2. Okay, that's all it is, okay? And it's already ugly like this, yeah? Okay, so that's in terms of ecology, that's not too complicated, right? But then if you try to solve this, you won't be happy, okay? And even with SymPy and so on, this is hard to solve, okay? Of course, there are some points some solutions that are easy, okay? So, of course, if all of them are 0, Okay, this is a fixed point. Yeah, we don't even have to check. Okay, if I don't have the consumers, okay, if I don't have the consumers, this is 0. Okay, C1 and C2 are both 0. Then all of these terms here are 0. Okay, and then I only have two logistic equations. So I have a solution with only R1 equal to A1, only R2 equal to A2, or with both of them at their carrying capacities K1 and K2. Okay, and no consumers. Yeah. So you see, we already have 4 fixed points, right? All zeros, only R1, only R2, both R1 and R2, right? So we already have 4 fixed points just by knowing something about the system, yeah? Okay, now we can see what happens with consumers, and now these are the ones that are already hard to calculate, okay? Then we probably will have a fixed point with only one consumer, then only with the other consumer, and these are, I already don't want to try to calculate by hand at all. And then we have the solution with, or maybe we have, maybe we don't, right? With all of the 4 species, okay? Yeah? And then what we're going to do, we are going to try and find all of them using fsolve, okay? So, yeah? So it depends on which are the initial guesses, okay? Which are the initial guesses. So this, I did this at home, okay? Because it's kind of boring, but then maybe I should have done this in front of you to see how I do it, because it's not magic, right? You just keep trying, going back and forth and, until you get a, well, you have to choose a set of parameters over here, okay? Okay, and then, okay, here I did something that is a bit smarter, because over there in the Ailey effect here, I put the parameters inside the equations already, okay? This is usually not a good idea, as you have are probably aware by now, right? Because you want to keep changing that later. And then we can also, with fsolve, you can also include this in the following way, right? It's exactly as you do with the, when you solve these differential equations. You see that this is exactly the function that you would have to have in order to solve this differential equation. Yeah, this is the right-hand side of the equations, okay? The only difference is that you don't receive t here, don't receive time. Other than that, everything else is the same. So if you have already implemented the numerical code, you can find the fixed points just by including t or not over here, right? Otherwise, it's exactly the same, okay? So you see, this function now receives an x that is an array, okay? An array with 4 values, and which will return the 4 equations, okay, as an array as well, okay? So I wrote this down. I don't think we want to go in detail about it. I just wrote down those equations, right? But now this is easy or not? Yeah, do I have to go over the equations or no, right? And you can do this, okay? And hopefully it's alright, right? So, yeah. Well, and then I have here a list of parameters, and then I will have a tuple here, a list with all the parameters in the correct order also, okay? And now I want to solve this using fsolve, and you see that I have to have the function here, then the initial guess, and then there's this argument called args, okay? That is just the list of parameters, of extra parameters after x, okay? So I just pass a list containing all of those other parameters, okay? Okay. But now I want to read over, so you see I have the carrying capacities here at 10 and 20, okay? So I want to read over all of the fixed points, okay? So maybe let's go step by step here. So it was like Ctrl Shift Enter. Yeah, to run just the selected thing, right? So if I run the first one here, you see I put all of the other 3 to 0 and put something only in the R1, yeah, only R1 different from 0, right? And then I get the, this is equal to 5. Oh no, I changed it. Oh, I was playing with this, I changed it. Those are not the parameters at all, right? So I changed it, all of the parameters later and did an update here, okay? So yeah, so, okay, ignore these parameters up here and use the parameters down here, okay? Because, yeah, I think my initial guess wasn't so good. So you see, I started with R1 equal to 10, but the carrying capacity was 5, so it arrived at this only 5 for the first the first one, okay? Then I do pretty much the same for the second one, and I get the second one with carrying capacity 8, okay? You see K2 is 8. Now I want with both, okay? With both resources, okay? So I have 0 for both consumers, and I have this, okay? Now, what if I want something that has only one consumer, okay? So I go and put 0 to the second consumer, but 1 to the other consumer, okay? And now we see that we have 0 for the last one. We have 0.5 here. We have a very low. You see here that this means that the first resource here is into extinction. Okay. Can you tell me why is that? Ecological terms, yeah.
Probably the attack rate on the first one is bigger.
The what?
Consume rate, the attack rate.
Yeah, probably, right? So this would be what is called apparent competition, right? Competition through predator. Yeah, if you have a single shared predator preying on 2 resources, then the resource that is more resistant to predation is going to survive, and the other is going to be eliminated. Okay, so you actually don't have this. You see, I expected one equilibrium with the resources and one consumer, but actually you find out that, well, maybe this doesn't exist. Maybe what happens is that with one consumer, 2 resources, one of the resources goes to 0 actually. Okay, so you don't have this fixed point. So maybe let's look at the other fixed point with only consumer 2. Okay, why am I saying that this is extinction? Because this is very close to 0. Okay, so this is 10 to minus 11. Okay. Now with the other one here, I have something similar, right? So this is now close to 0, okay, 10 to minus 14. I have here 0.35 for the second consumer, and now the first consumer is at 0.8, but the second is going to 0, right? So I chose the parameters in such a way that here one of the consumers prefers one resource, and then the other prefers the other, and then the one that is preferred is the one that goes extinct, right? So, yeah. And finally, let's see if we can find something with all of them together, yeah? Yeah, and you see, there is such an equilibrium, you see? With all 4 species together, okay? So, having the 2 consumers means that now none of them are doing extinct. None of the 2 resources is doing extinct. Nice? Yeah? But then what does this mean for the system itself? So we can also, and we already have written all of the equations here, so we can go and see what happens as a function of time. Okay, we can solve numerically these equations. Okay, then you see, I copied exactly the same function over here. I just added this t here in the list of parameters. Okay, everything else is the same. Now I set an initial condition, a list of times. I had to include this because the system was giving me some integration headaches, okay? But when I run this, what I see? I don't see an equilibrium at all, right? I see cycles, right? Because this is consumer resource with type 2 functional responses and so on and so on. So there are cycles. Maybe if I run a bit longer, maybe let's go up to time 1000. Yeah, I think those cycles are not going away, right? Yeah, they look pretty periodic to me. Yeah. Okay. Question.
Can we see that log scale?
Log scale,
just
sure.
out of curiosity.
Oops. Yeah. So the minimum for the second resource is kind of low, right? So 10 to minus 3, but yeah. Okay. Nice. Yeah, so you see, we found the fixed points, but actually the solution is not, let me go back to the linear scale. But actually the solution is oscillatory, okay? But you see that they are oscillating, but they're oscillating at levels around this last fixed point here, okay? So you see that R1 is a bit larger than, let me read again so we can see more clearly the values here. Okay, so you see that R1 is usually larger than R2, but not so not too bad, not too much, right? So, and then C1 is also larger than C2, and so on, okay? So this is, usually the green line is above the red line, you see? So C1 is coming out better here, okay? So far so good, questions, comments? Okay, so this kind of simple, okay? Kind of simple, okay. There's an so these are only 4 equations, right? So with few equations, right? So I don't know, up to maybe 10 equations. There's no specific threshold here, but then with few equations, F-solve is a very good tool. But if you want to go to the tens or maybe hundreds of equations, then F-solve is not a good idea at all, right? Because it's not very efficient for very, very large systems, okay? Then you use another method instead of F-solve that is called the Newton-Krylov method, okay? Newton-Krylov. That is pretty much the same. The only thing that I don't like about Newton-Krylov is that it doesn't have that RDS parameter that we had here, okay? So you have to do funny stuff like you write this out, and then you have to define your parameters beforehand and not as arguments over here, right? So this is, yeah, you could kind of define a function that receives the arguments and that defines this function. So I have to do some trick here to pass the parameters in some way, okay? But it doesn't receive an additional list of arguments, okay? But other than that, it's pretty much the same. You pass the function that now receives only x and returns, and also an initial guess, okay? And it will give you some of the solutions over here. You see? So I think that those are pretty much the same, okay? So we would go back and try to compare, but I think these are the same, yeah, the same numbers, okay? Okay, so Newton-Krylov is then a better way, right, to solve very large systems. 4 is not very large, right? So 4 is, but then we want to do this for the Fisher-Omorodov equation, okay? So what do you do, right? So let's go back a little bit to the board, right? So, so you remember that when we were discussing this, right? What did we have, right? Instead of having the method to solve this was we had used the method of lines where you put a lot of points here, okay, and then you had an array of points, okay, and you remember that to simulate diffusion, you have that the points always exchange individuals with only the neighbors, right? So you had that stuff where for each point I subtract 2 times itself and sum the 2 neighbors. Remember that where we had the idea of summing the shifted arrays and so on, right? So if you have that, you already have the whole right-hand side of this equation here, right? So what we use to implement is we discretized this in space and wrote down the right-hand side of this equation. So we already have that. We just have to tell the solver now that we want all of them to be 0, yeah? So, this will be a little bit complicated, but since we already have the implementation for that, this is pretty simple, right? So what do? I go over our previous, so what was it? Yeah, the reach up at size here. Remember that we kind of went back to this yesterday, yeah? So we already have this function here. You remember this? That was working, yeah? Was working. So this returns the right-hand side of that equation, yeah? So I just take this function here that gives me the right-hand side, and I copy over there. And now what I want to do is just ask for which values of x, of the array x, this whole thing is equal to 0. Yeah? Makes sense? So, so that's what I'm going to do here, okay? So I just take it from the other one over there. Since I'm going to use Newton-Krylov, I cannot include the arguments over here, okay? I have to set them up before. And it's exactly the same code, you see? I just have to take out the dependence on time and on the parameters, okay? Yeah, so there's a lot of stuff here already, but it's exactly the same function that we had written before, right? So, and now I want to, well, now I import Newton-Krylov again. Okay, and then I just give an initial guess what is the initial guess here? Well, the carrying capacity is equal to 10, so I just try to put a constant where the whole solution is equal to the carrying capacity. Of course, since now we are using absorbing boundary conditions, we know that this cannot be a solution because at the borders it has to go to 0, okay? But well, the solver will have to sort it out, yeah? Okay? And then we just pass this to the Newton-Illovy function, okay? You see that I chose here n equals to 100, you see? 100, so it's a lot of points, yeah? So this is a system with 100 variables, 100 equations, yeah? This looks pretty hard, or not? Solving a system with 100 equations, yeah? Yes or no? What do you think? Difficult numerical problem or easy? Yeah, easy, right? Yeah. So this is much quicker to run than solving the system in time, okay? And now I have this UEC here, equilibrium here, that I just solved it. Instead of printing it, I'm going to plot it, okay? I'm going to plot it over the grid of space, yeah? And this is the solution, okay? Nice. Let's check that. How about that? Yeah, so we can run the program again with the same set of parameters, okay? And see if the final solution actually gets close to this, okay? Yeah, so let's do that. So now we have the same function, but now with dependence on time and the parameters, okay? But other than that, it's the same thing inside. We set here the same parameters, I hope. Yeah, the same parameters. And now I run this over time using OG_int, okay? So I'm now running over time, okay? Yeah, and I get the solution and then plot the two of them, okay? I plot the two of them. So in blue is the equilibrium one that we found using this stuff here. In orange is the final solution. You see I plotted the final solution at the last time here, you see? As a function of space, you see? And it's pretty much the same, yeah? So maybe if we want to compare in more detail, perhaps we would, instead of plotting the two together, maybe plotting the difference. What about that, yeah? And then we can see if they're really, really equal, yeah? So maybe let's plot the difference, okay? Funny. You see that the difference between them is not 0. You see, it's close to 0, but it's 0.006 here. Okay, so, but what is funny is that there's still this shape. This is exactly the same shape, right? So it's not random, right? It's not numerical error because it has the shape. Okay, so it probably means that one of them is not very accurate. Okay, so which one is not accurate? I would guess that maybe we should go for a longer time, right? Because this runs over time. It approaches the equilibrium solution, but maybe we didn't wait long enough for it to get right at the exact point. So instead of running for only 20 time steps, maybe 200, okay? And let's see if this, well, this is going to be the same, right? Yeah. I cannot distinguish them both here, right? But if I plot the difference, now the difference is around 10 to minus 8, right? So it's a lot smaller, and there's no clear pattern here. Well, it's kind of weird pattern, yeah? Okay, so this means that inside the accuracy here, we already had pretty good, very close to the final solution. Nice? Yeah, questions, comments? Yeah, so you have noticed that I didn't pass you any exercises today, yeah? So I want you to, yeah. I don't know if this was a good idea, but I want you to finish here, okay? I want you to finish here. So our thought about this specific thing. Well, I want you to just comment very briefly that this looks like a kind of cheap trick, right? So I just found the equilibrium solutions and so on, but for many systems, right, especially when you have, when you don't have predator-prey oscillations, right, if you only have competitive interactions, right, you are almost always going to have that solutions due to an equilibrium, right? They're usually stable, they don't oscillate. What did I do here? Well, okay. Yeah, so usually the solutions don't oscillate, and then in competitive systems you are pretty much always guaranteed to end up in an equilibrium. Okay, when you have consumer resource, then it's complicated. Okay, sometimes it goes to equilibria, but sometimes you go to cycles. But even as I told you, even when you have cycles, when you do have cycles, you more or less learn a little bit about them because they have to oscillate around deficit points. Okay, so if you know deficit points, even if this is a distribution space, you know that your oscillations have to oscillate around deficit point. Okay, around that equilibrium. Okay, and the thing is that for many problems, you are often interested in this final solution, right? You don't necessarily want to look so much at the dynamics, okay? And this makes a lot of stuff really easier to study and analyze. I have done a lot of stuff that would be hard became simple because of that, okay? So this is a nice technique, okay? Okay, comments about this? Yes.
So our boundary conditions, in the end of the day, are always expressed inside the function that defines the differential equation, right?
Yeah, exactly, always. Because it's what we have discussed very briefly, not so briefly, but yeah, in the, I think it was in the, when we were talking about reaction diffusion, okay? This idea that depending if you have no flux boundary conditions or absorbing boundary conditions, the equations for the first point and the last points are going to be different, right? And then you have to work out what they are like depending on the boundary conditions, but they are going to be inside your function, yeah? Of course, you can, what you do sometimes is that you can, instead of having to change this every time, okay, because maybe this is what you're worried about, right? You have to go and change by hand every time you want to change the boundary condition, yeah? So, but you know, of course, this is something that is very usual to do as well, although I didn't include here. You could do something like, okay, I'm going to say that my boundary condition is something like A times del n del x at x equals 0 plus B times n at x equals 0 equals some constant C, okay? And then you say that A, B, and you write your boundary in terms of A, B, and C, and A, B, and C become parameters of your system, okay? So if you set A to 1, B and C to 0, this is a no flux boundary condition. If you set A to 0, B to 1 and C to 0, this is an absorbing boundary condition. And if you set A, B, and C different from 0, A and B different from 0 and C equals to 0, you have what is called a robbing boundary condition, that is a partially reflective boundary condition. And if C is different from 0, it means that you have stuff coming from outside, even when you have no population inside, okay? So, so you see, instead of having to change your equations every time, you can write some form, some general form for your boundary condition and have these numbers be parameters, okay? So maybe this is what's worrying you, that you have to keep changing every time, yeah? Okay, yeah. More questions? Okay, so yeah, so I think the course stops here. I want to ask you if you have more things you want to ask, right? Because we have a lot of corridor talk, okay? Corridor talk, but maybe we can, you know, discuss with the whole class and see what are the stuff that is left out, okay? So. So I will talk about a few things that people have already asked me about. So the first one is stochastic equations, right? So stochastic equations, they're not too hard to integrate numerically. Okay, so the real difficulty with stochastic equations is that each solution, well, they don't even call it a solution actually, right? So each realization of a stochastic equation is just, what are stochastic equations? They look like differential equations, but they have a component of noise, okay? And noise is like a random thing, okay? A random thing. So each time you try to simulate it, it gives you a different solution because the noise at each time is a little bit different, okay? Or, yeah, depending on luck, okay? So, yeah, so it's random, right? So each time you solve it, each time you simulate it, you have a different solution. Then what is really called the solution, the full solution of a stochastic equation is no longer a single simulation, right? The full solution of a stochastic equation is the distribution of probabilities of the trajectories over time, right? So you see, I could have something like, I would have, okay, I run once and I get something that goes like this. I run it again and I get something that is like this. I run again and I get something that goes like this. I run again and it does this, and so on, right? And if you run this a lot of times, like thousands, tens of thousands, I don't know, you'll see that at each point here, maybe I have a distribution. I have a distribution of values after some time, you see? So you have a distribution of values, a probability distribution for each point in time. It's actually a distribution of probability over trajectories, right? So this is a kind of complicated object, you see, to handle, right? So this would be the full solution of the stochastic equation. Often we can only find this analytically for the simplest models, right? So, but what is usually easy to do is calculate the average or the mean trajectory. What is the mean trajectory? The solution of the deterministic equation, right? So most stochastic equations have a deterministic model that represents the mean trajectory, okay? The mean is easy to do. The full solution is very hard to do, right? So usually you just run a bunch of simulations, take an average, and calculate the standard deviation, and so on, and this is more or less happy with that, okay? But this is running a lot of simulations here, this is very time consuming, but the method to simulate each of them is very simple, right? So it's pretty similar to the methods we use it to solve this, okay? But then you have to take the results of many simulations and put them together and so on. This is kind of tricky, okay? Yeah, so it's not, in numerical terms, in computational terms, it's not too large a gap, okay? The thing is that it takes a lot of time to simulate all of this, okay? And it's tricky to deal with the solutions later. Okay, yeah, so this is, yeah. There's a conceptual gap that is a bit harder, is this idea that the full solution is not a trajectory, it's a distribution of probabilities of trajectories. When you try to write this down mathematically, it gets, yeah, it's a bit tricky, you know, so, yeah. Okay, stochastic equations was one of the big questions. Yeah. Does someone want to ask something? Yeah?
It is about the languages. Why Python?
Why Python? Okay, I talked very briefly about this in the beginning, right? So in practical terms, right, is because I use Python a lot, I like Python a lot, and I'm happy with that, right? So it's like, well, if you know, professional researcher in the field use Python, then it should be okay, right? But then there are other considerations. First is that it has a quite comprehensive ecosystem in terms of it has packages to do pretty much everything you want to do. Outside of, well, not in statistics, R has a lot more, okay? So for statistical applications, you'll probably be happier using R, okay? Python also has a lot of statistical modules and so on, but I think R is really the standard in statistics, okay? But Python has a lot of packages that you can use, has a lot of tools, it's easy to, and the thing is, I like it because it has this philosophy that you have a basic set of tools and then you build on top of that, right? So I think Python is a good way to learn to build a bit your own tools on top of the existing stuff, okay? So you see that to solve this, the problem that we just talked about today, okay? I didn't have to program Newton-Krylov by hand. Newton-Krylov is a basic function, and from the name, you see, the method is not new at all, okay? It's a standard method. But then there was no package for my particular problem, right? But if I know that, okay, this particular problem, I can solve with this method, it's easy to build from that, you see? So there's this philosophy of having all the basic methods implemented, but then there are specific problems you just build a small program on top of that, okay? So this is, I think, it gives you a lot more freedom than having, for instance, I would have a package that gives me directly the stationary solution to a PDE, okay? You would build that package. But I have never seen that package in Python before because people don't value it, right? So the philosophy, the culture is that you have the basic methods and not and applications you build for yourselves. And then this is nice. This looks like okay, but this is more work. But no, but it makes a lot more flexibility. You know, once you learn these methods, you can do a much wider range of applications than if you only knew a single package, because a single package is never enough for all applications, okay? So this is another point that I like about Python. Of course, there are intrinsic characteristics of the language that I like. It's that it's easy to write, easy to read, at least from my point of view, right? I don't know. It would be much harder to do this in low-level languages, right? So I don't want to go into C, Fortran, C++, all this stuff. I could have done this in R, perhaps, yes, perhaps, right? But this is, I discussed this a bit with Paulo, but we decided, yeah, I decided actually, right? So it's my decision, right? So, yeah, but I discussed this with him, and I think it was okay to not use R and use Python instead, even if it's two languages instead of one, but yeah, I think things are numerical computation in Python. I think it's a little bit cleaner. Yeah, is that enough? I'm not sure, because there's another stuff that I also tell my students when I do numerical calculus at the university, right? As a regular course, a lot of them go to engineering, not to science. This also helps if you want to get a job in anything else outside of science, okay? Because Python is very useful in all areas of computing, okay? So, yeah, but maybe that's not a good point for you specifically, yeah? Yeah.
Hi.
Hi.
So, I wanted to thank you for the course and say that it was very difficult for me. I still didn't fully get some of the concepts, but I'm like calmer now because I know that I have time to look at the exercises and understand this better. And about Python, I wanted to say that I do see the value, because sometimes when we read other papers, the code is published in Python, and then it's good if we at least know how to read it. Though I do think R is more familiar to everybody in biology, I guess. I do understand that it's important for us to know, and also that it is important for us to know how to build things from scratch, although it is very, although it is very difficult. And I'm gonna say this, as a GIS user, like I use QGIS, ArcGIS, and sometimes I've spent a lot of time looking for a package in QGIS, and then it was much, much easier to just do it directly on R, or to just write in Python inside of QGIS. So for those who work with geographical data, that's a real important language. So thank you.
Yeah, okay, more comments then. more comments. Okay, so this was why Python. So let me talk a little bit more about Python, right? So but our introduction to Python here was pretty basic, okay? I didn't get close to covering even the basic aspects of Python. So there were types of objects or in structures in the language that we didn't see at all, right? So you would talk about dictionaries. We didn't talk about input, output, right? So how do you write to a file? How to read from a file? How do you get data from a web page? How do you download something from a server? How do you, right? So all these input, output we didn't cover at all. We also didn't discuss stuff like what about custom types of objects, right? So one of the strengths of Python is its object orientation system. Okay, so this is, I don't know if you have heard about object-oriented programming, right? So OOP. So OOP is very well done in Python. It's very nice. And then I didn't talk about this kind of stuff at all, like classes, how to write custom classes and so on, right? So if you have never heard about this, just filter it out, okay? But this is a more advanced feature of the language that I didn't talk about at all. You should have another very nice thing about Python is it does have a library called pandas that is used for analyzing data, right? And I didn't go over that at all, right? Because we didn't need for this course. In a sense, this was just a subset of Python that was the parts that we needed to use for this course, right? But there's a lot more stuff to learn about Python, okay? We're not really exhausting even the basic Python, okay? So there are other stuff to learn, okay? Then there's another issue talking about a few of the holes, right? There's another big hole in the course that is, I didn't talk about how you document your code and how you publish your code, okay? So these days, it's pretty much standard to put your code up on the web using what is known as version control system, okay? So like Git. I think these days Git is so dominant that people don't even talk about the others, right? So, but back in my day there was Subversion, Mercurial, there are other options, okay? But these days it's pretty much only Git, okay? Do you know what I'm talking about? Have everyone heard of Git? Git, yeah, this. Let me spell it out, yeah? So, yeah, Git, like this. So that is a system that controls the versions of our program. So if you have an initial version, then you make changes, it remembers which changes you made over time, right? So you can keep track of all of the changes. This is especially useful for software developers because, you know, you have all these updates, and then if your program depends on other program, and the other program is changing, and your program is changing, then you know which change happened when, and make your code. This version of your code depends on older version of the other code, and your newest code depends on the newer version of the other code, and the Git makes this process a lot easier, right, to develop code both depending on their code, but also collaborating between different people, right? So if different people are changing the same code, how do they do it so that they don't change code in a way that they're incompatible, right? So the code doesn't work anymore, right? So this is also done using version control systems, okay? Version control systems, okay? So this is another aspect that is pretty important. I think there will be a lecture about it from some of the lecturers. I think it's a single lecture at some point, okay? I don't know who or when, right? So, but I think there will be something like that. Yeah, and when I tell documentation, do you know what I mean by documentation? Yes or no? It's like writing up your function, right? If you want to, this here, this stuff here is inside a notebook with a lot of text, okay? But if I have only the code, only the Python code, and the code is just this stuff here. Sorry. Yeah, of course. Yeah, so here you have a lot of text, okay? A lot of text explaining what is the mathematical problem that you're solving, what are the parameters, and so on and so on. So this is pretty much well documented, okay? Because you have the description of the problem, and the parameters of the problem, and the method to solve the problem, all described here, and then follows the code. But if you only have the code, a Python file, with only this inside, imagine that you just have a file starting here and ending up down here, okay? It's hard to know what the code does, right? Yeah? And if you're not familiar with the problem, what does R, K, G, and so on means, right? So if you want to publish code, especially if you're going to build packages, you have to tell people what your code does, what problem it solves, what each of the parameter means, okay? So you have to build this inside your program. So this is the documentation of your program, okay? And there's specific ways that you do this, right? It's not just with comments, because for instance, remember that I had told you about the help function. Remember this? So I don't know, let me look at the help for Newton log, okay? Oops. Okay, this is not the one I was running, right? So it doesn't know this function, sorry. Yeah. It was over here, right? So, yeah. Yeah, here it is, the help function. You see that there's a lot of detail, okay? So it tells me what it does, the kind of method, why, for which kind of problem this method is nice, and so on. It describes each of the parameters, even the optional arguments, and so on. You see, so there's a lot of detail over here, yeah? A lot of detail, what object it returns, and so on, when it raises an error, other related functions, notes about the mathematical problem. You see, this is written for, this is LaTeX, right? So in the web, this renders as mathematical notation, okay? And even references for the methods themselves, or papers where the method was described, and then a few examples even. So this is a full documentation, you see? If I have defined also a function called FKBP, right? Yeah? If I look for the help for that function, well, this is a function that I just wrote over here, yeah? Oops, no. FKBP, what is the help of this function? Well, nothing, you see? This is a very poor documentation, you see, because it doesn't tell you what the function does, what the parameters mean, and so on. And there are ways to make the documentation appear here when you type help function, you see? So I didn't talk about this at all, but this is important in practice, okay? Yeah? Okay, what else? More questions? Think about what we would be talking about in the corridor, right? Just after the class, so you can ask inside the class as well. Yeah. Your curiosity died in the last few minutes, yeah. So, yeah.
Okay, first of all, I'd like to really thank you for this course. I am someone who didn't know a single thing about Python before coming here, so it was a real shock therapy. I'd say it was completely new, everything was new. It was a real fight against the code to understand it at the start. And one thing I think I appreciate most of all of everything you did for us was really those notebooks, because I can make copies of them, I can check them on whenever I want, and I can use them to study by myself from now on as well. So I think this will help me a lot in the future as well. So I'd like to thank you for all this work, because it was over, did it reach 20, I think?
Sorry?
20 notebooks of those.
Almost, right? I think there were a couple that we used it for 2 classes. I think there was something like 16 or 17.
Yeah, I really appreciate the hard work on those, because I know you probably spent a long time doing those, I suppose.
Well, pretty much every day a notebook, right? So
yes.
yeah.
So really thank you.
What do you do from midnight to
oh my God.
sometime in the early hours? Yeah.
I think like a question I would make is since you said yourself there were many basic things of Python in general that there was no time to cover in this course. If I were to search for that information for myself, I don't know if you gave this preparatory material before the course started, because
No.
I just went straight to calculus and mathematics basics, because that was my
didn't have time
weakness.
to go through anything else.
No
Yeah, of
time to
course.
check Python. So I ask, if I were to search those information by myself, is there any sort of article or website that you would recommend for us to search these things by ourselves?
I didn't recommend anything specific, because courses on Python, there are so many on the web that I wouldn't even know what to recommend, right? Because I haven't read those in a long while, right? So back when I learned Python, this was like 12 versions of Python before in 2007 or something. There was a pretty good one that I think is still around. But I'm not so sure if I recommend that it's all dive into Python, right? So this is the material that I use it, but it's more focused on programmers than on scientists, you see? There are a lot of Python courses for data scientists that will cover data analysis, pandas, more complex plotting and so on, and a bit of statistical methods, I guess. Because Python is such a general language that you'll see Python courses for web developing, Python courses for databases, Python courses for... There's always Python courses for this and this and that. And then there are general Python courses, but there are so many of them. If you look at the web, the problem that you're going to have is not finding, it's choosing, okay? So this is the hard thing. One thing that I really like is that Python has a very clear tutorial itself, right? So in the python.org, the official Python documentation is pretty good and pretty complete, okay? The issue with complete is that it's very long, yeah? But also even the official Python documentation is pretty good. I don't know, I think this is a question that maybe asking for colleagues where they learned it, or looking at the web for reputation of courses and so on. I think it's probably better, because I learned Python so long ago that I don't know really well the material around in the web now, you see? So, yeah. So I don't have any specific recommendation. So yeah, if anyone, do you have one?
There's the book that Joshua Weitz recommended us. That is Student's Guide to Python for Physical Modeling.
Okay.
There was a lot of good stuff there.
Yeah, could try that. Yeah. Did I answer all the questions? Yeah, okay, good.
That's just another recommendation. It's a YouTube channel called Python para Zumbis. And there's a specific course for like women in science. There are courses, I guess, for some fields. I think the guy works with a little bit of biology. I'm not sure, but the classes are good.
Yeah, I think there was one by a group of biology that is, I think, called data carpentry. I think it's something like that, data carpentry. But this is towards data analysis, right? Yeah. Okay, more questions. More questions. None whatsoever. Yeah, do I have to invent my own ones? Yeah. Yeah, question. Or you just took the mic? Okay, no. Okay, so yeah.
I don't know if it's too general, but when we looked into symbolic Python, I felt like there were some limitations. So I wanted to know what are the limitations you would say about symbolic solving things.
Well, symbolic computation has limitations, but I wouldn't know how to define them, because it's like, okay, it has the ability to solve systems of algebraic equations, right? But then if you try to put the one that we solved in the class today with 2 consumers and 2 resources, it's probably not going to be able to solve that for the age with 4 species. Probably, I didn't try. But probably it's not going to. Why? Because it's too complicated, but then there are other complicated equations, even with 4 equations, that sometimes it does solve, right? So what is the difference between the ones that it's able to solve and the ones that it's not able to solve? I don't know how to easily tell you, well, this class of equations. There is something like that, okay? So people that work on this professionally, right? The people that code those libraries, they have a whole math. There's a whole math behind this. And there are classes of equations that are solvable and some that are not solvable, or that require more sophisticated techniques to solve. But I don't know anything about that, right? So I cannot really tell you, right? So this is, I mean, you know, you probably need courses on advanced algebra to talk about this, because you have to know about stuff like, I don't know, rings of polynomials, and a lot of complicated stuff to deal with that, okay? So, yeah. And also the same for other stuff, right? So for integration, it's pretty much the same. Some integrals you can do, some you cannot with certain methods, and so on. So it's, and some stuff it's possible to do, but it's just not implemented yet, right? So in a sense, I think SymPy has it's less well developed, it's newer, right, than Mathematica, okay? So there's stuff that Mathematica has implemented and works that SymPy doesn't, okay? But it's kind of rare to, at least in my experience, it's a little bit rare that I want to solve something that SymPy can't and Mathematica can, right? Yeah. But it's possible. Sometimes it happens, yeah. Okay? More questions? There was something I'm going to talk about. Okay, in the examples here, I used mainly age structure for this last part of the course, right? For reaction diffusion and advection in the last class. I mainly talked about population in space and age structure, okay? There are a lot of applications of this also in evolutionary dynamics and evolutionary dynamics. I didn't go into these applications because we are going to have 2 courses about this, right? Yeah, I think Joshua's course is going into this. Then there's an evolutionary game theory later. So a lot of classes already dealing with that. And then I think building the theory, I think is more complicated, right? Because, yeah, so I left it for other classes, but these are very, very interesting examples, okay? Yeah, so this is a question that I'm answering myself, right? So it's your turn again. Yeah? Yeah.
I remember that at some point at the beginning of the course, you said that there are a lot of programs that use Python. We use the Colab to not have problems with different programs. I think it could have some problems. I don't remember very well. But like using Python from different programs, each one uses their own. So in order for everyone to use the same, we use the Colab notebooks, if I'm not mistaken.
Yeah.
But I was curious about if I was, in my case, I never used Python before this course. If I were to choose a program outside the Colab notebooks, which program would you recommend for Python?
Okay, so, well, hard question. That's a hard question because everyone has its personal preferences when it comes to coding and programming interfaces and so on, right? So, if you like the RStudio interface, okay, that interface where you have your editor here, your shell over here, the variables in the right-hand side, and here I have some space for plots and so on. You are pretty much going to find something similar using an interface called Spider, okay? Spider, right? So this is a good one if you like RStudio, something that looks like the RStudio interface, okay? Of course, you can also run the Jupyter Notebook on your own computer instead of in Google's clouds, okay? So this what Colab is actually just the Jupyter Notebook, okay? But on the cloud instead of on your own computer. But you can run also something that is exactly the same as Colab, but on your own computer, okay? This has some advantage because you use your own machine, and maybe your machine has more computing power, more memory than Colab's has on the cloud, okay? Now, if you ask me what I personally use, it's not something that I generally recommend, okay? I use something that is called an IPython shell. IPython shell where I run the code. IPython shell. That is just the shell. You know in RStudio where is the shell that runs their code. IPython is just such a shell, okay? It's a shell with some advanced features, but it's still just a shell. And then I just run the code in the shell, and I just edit the code in an editor, a regular text editor that is VIM, okay? This is a very roots, yeah, you see, very roots approach, okay? This is a advanced editor. I don't recommend it for beginners because it has a very sharp learning curve, you know. So yeah, you open it, and if you have never used it before, you don't know how to quit the program, you know. So yeah, there's no buttons to appear. It's not friendly, okay, but it's nice, but it's not friendly. Yeah.
Oh, I just wanted to say that if you Google Anaconda on the web, you can find basically a package in which you can install both Spider and Jupyter Notebook at once, I think.
Yeah. How do you install this stuff? I think this I told you in the beginning of the course, right? You don't want with Python, because in R, you install RStudio and you can install all of the packages from inside R, right? In Python, this is a bit suspicious, right? Because it doesn't work so well. So what you want is to have install in your system all of this stuff in your system itself, not from inside Python. So this is why there are these packages like Anaconda. I think Anaconda is the most famous, but it's a very large package, right? So this is called Anaconda. Anaconda includes Spider, includes Jupyter Notebook, includes IPython shell, includes all the libraries you have seen, SciPy, NumPy, Matplotlib, Pandas, and SymPy, and many others, okay? But it's a huge package, okay? There are several gigabytes of, because there are like so many packages that you have never heard about and you never use, yeah? There's another related package that is called, you can install just Conda, okay? Conda is a diminutive version of this that has only a few basic packages, and inside Conda you can choose to install just some things that you want, okay? Just the stuff that you want. If you have, if you are low on disk space, maybe use this one, yeah. Yeah, I think there are other options as well, right? There's another notebook that doesn't run inside the browser. That is called a Qt console. I think this is not very popular anymore, but it was used for some time. Yeah, there are other options, right? So then, I think these are the main ones. Okay, so yeah, and of course this combination here, I really like it. You can replace VIM with your preferred editor, right? If you use, I don't know, VS Code or I don't know, Notepad++, that kind of thing, right? So any editor is going to work, okay? More questions? Okay, so maybe it's time to go. Yeah, so, yeah, okay. So, well, thank you for, I think it was, I had some fun, right? I don't know about you. Yeah, so the thing is, you have to have some fun, okay? So, yeah, I hope you have learned something useful and that you had a bit of fun as well, yeah? Okay, so thank you.